Okay, so in this video, we will discuss a classic recursion problem, Towers of Hanoi. Okay, Towers of Hanoi. Now let's see what this problem is all about. You will be given three pegs. You will be given peg A. You will be given three pegs. These are known as pegs. Okay, so you will be given three pegs, A, B, and C. You will be given three pegs, and you will be given n number of discs on peg A. There will be n number of discs. There will be n number of discs on peg A. N number of discs will be present on peg A, and you will have to transfer these n discs from peg A to peg B with the help of peg C. This is the Towers of Hanoi problem. But while transferring discs from peg A to peg B, you will have to keep two constraints in mind. Constraint number one, you can only move one disc at a time. You can move only one disc at a time, only one disc at a time from any peg to other. So if you're moving a peg from A to B, you will be moving only one disc. So if you're moving a disc from peg A to peg B, that will be only one disc. If you're moving a disc from B to C, that will be only one disc. So at a time, you can move only one disc from one peg to another. And the second constraint is a larger peg, or not a peg, rather a larger disc, right? Not a larger peg, a larger disc. A larger disc can, okay, let's put it this way. Let's put it as a negative case. So a larger disc cannot be over a smaller disc. A larger disc cannot be placed over a smaller disc. Okay, a larger disc cannot be placed over a smaller disc. That means what you can do is, so this is the largest disc. The largest disc will always be at the bottom. Now above that you will have the second largest, above that the third largest, and so on. That means the smallest disc will be right at the top of the peg. And one more thing, you cannot take out any intermediate disc. That means here, if I assume, for a moment, if I assume that there are exactly three discs, for a moment, if I assume that there are exactly three discs on peg A, then I can only move the topmost disc. I cannot take the bottommost, or I cannot take any intermediate disc. I cannot do that. I can only take the topmost disc and move it from one peg to another. So these are the constraints that we need to keep in mind when solving the Towers of Hanoi problem. So what I'll do is I'll take up an example for n equal to 3 discs and show you how the movements can be done from one peg to another so that the problem can be solved. Now let's see this case where you have been given 3 discs on peg A. So n is equal to 3 because n denotes the number of discs. So here the number of discs on peg A is 3, and you have to transfer these 3 discs from peg A to peg B with the help of peg C, keeping the 2 constraints which I pointed out in mind. So we'll do this step by step. Let's see how this problem can be solved. So step 1, what I'll be doing is I'll be showing you the steps in a single diagram, but what I would urge you to do is for every step you please draw this diagram separately. Okay, here due to lack of time and lack of space, I will be showing all the steps in one diagram, but you, for your examination purpose, please show every step clearly with the help of proper diagrams. So step number 1 is, what I'll do is I'll move, what can I move? I can move a disc. So I'll move a disc from A to B. So move A to B. So move A to B. This implies that move the topmost disc from peg A to peg B. So if I do this, what will happen? The topmost disc which is present here, which also happens to be the smallest, the smallest disk will be moved from peg A to peg B. That is step number 1. Now, step number 2. In step number 2, what will I do is, I will move from A to C. So, I'll move from A to C. So, this will take my second largest disk. This will take my second largest disk and place it on peg C. And place it on peg C. So, that is step number 2. Now, step number 3. In step number 3, what I'll do is, I'll move the peg on B to C. So, I'll move from B to C. So, this will take the smallest disk from B to C. Now, peg C is empty. Now, in step 4, see, peg B is right now empty. So, at this point, what I can do is, I can take the largest disk which is on peg A and transfer it to peg B. So, that would mean my major problem of taking the largest disk and placing it right at the bottom of peg B has been solved. So, I'll take the largest disk. So, this will be, I guess, this will be step 4, I suppose. Yeah, this will be step 4. So, in step 4, what I'll do is, okay, just give me a minute. Yeah, so as I was saying, in step 4, I'll move the largest disk from A. So, from peg A, I will move to peg B. So, this will take the largest disk on peg A and transfer it to peg B. So, my peg A now becomes empty. So, that is step 4. Now, step number 5, look at this. Now, in step number 5, I will take the smallest disk and put it on peg A. Why? This will enable me to take the second largest disk and put it on peg B. So, I'll take the smallest. So, I'll move from C to A. So, I'll move from peg C, which contains the smallest disk, and I'll place it on A. And this will enable me at step 6 to move from C to B. So, this will cause the second largest disk to be placed on peg B, rendering peg C empty. And in the last step, which is step number 7, I will take the smallest disk from A. So, I'll take the smallest disk from A and move it to B. As a result, my problem of transferring 3 disks from peg A to peg B has been completed, right? Now, what I'll do is, I'll take up a couple of mathematical expressions to show you how you can calculate the number of movements as well as the number of function invocations required to solve this problem. And before going into the mathematics, I will first propose the algorithm for Towers of Hanoi. So, let's have a look. Okay, let's look at the algorithm for Towers of Hanoi. So, here TOH stands for the function Towers of Hanoi, and it takes in as input the number of disks denoted by n. These are your pegs x, y, and z. And now, what will you check? You will check that if you have at least, okay, this will be n, okay? This will not be x. Sorry about that. This will be n. So, I hope you have paused your video. Just pause the video for a moment and copy this down. I hope you have copied it down. Now, see, you check. If you have at least one disk, so if you have at least one disk to move, then you can take this task of moving disks from x to y and you can divide it in terms of moving n minus 1 disks from x to z using y, and a trivial step of moving one disk from x to y and the remaining n minus 1 disks from z to y using x. So, I'll repeat again, this entire problem of moving n disks from x to y can be divided into 2 subproblems. The first subproblem is of moving n minus 1 disks from x to z using y, and then, so where are your n minus 1 disks? Your n minus 1 disks are here on Z. And the next sub-problem is that of moving the n-1 disks which are on Z to Y using X. And there is one trivial step of moving one disk from X to Y. So this problem of moving n-1 disks from peg X to peg Z can be solved recursively, as well as this sub-problem of moving n-1 disks from Z to Y can also be solved recursively. That's why you see invocations to the Towers of Hanoi function itself. And it also involves one trivial step of moving a disk from peg X to peg Y. So I hope you have understood this algorithm. Now what I'll do is, based on this algorithm, I will propose two recurrence relations, one for finding the number of movements and the other for finding the number of function invocations. Okay, from this algorithm, what I've written down is two recurrence relations. So this is the first recurrence relation where I of n, this denotes the function for, this is the function for invocations. So total number of function calls or invocations. For that you have I of n, and m of n is for the number of movements. M of n is for the number of movements. Okay, so I of n is for the number of invocations, that means the number of calls to the Towers of Hanoi function, and m of n is for the number of movements, like we saw where for every step we moved a disk from one peg to another. So how many movements are there for n number of disks? We want to find the formula. For that I have proposed two recurrence relations. Now you can pause the video and copy down the recurrence relations. Now let's try to understand why I have written what I have. So for I of n, I have written 1 plus 2 into I of n minus 1. That means you can see that there is one invocation where you have to solve the problem of Towers of Hanoi on n minus 1 disks, and there is another invocation where you have to solve the Towers of Hanoi problem for another n minus 1 disks. So this is one sub-problem, this is another sub-problem. So you have to solve two sub-problems. For that you have 2 into I of n minus 1. Why n minus 1? Because you have to do it for n minus 1 disks. So here you have n minus 1. And what about this one? This one is for this trivial step of moving one disk from X to Y. And what about, and this will happen when n is greater than 0. That means when this condition is satisfied. When this condition is satisfied, you are having at least one or more disks. So for n greater than 0, this is the condition. And if you have no disks, if you have 0 number of disks, then there will be exactly one invocation. What will this invocation be about? This will be the invocation made by, let's say, your main method to the Towers of Hanoi function, and it passes a value of n as 0. A value of n as 0 is passed. Now, since this condition is not satisfied, it will not enter the body of the if. So there was only one invocation, and that invocation was of the function TOH itself. As a result, if you have no disks, you will have exactly one invocation, and that is of the function TOH itself by a main method or by some other function. And let's look at this recurrence relation now. This is for the number of movements. Now again, just like for the number of invocations, this part is same, right? That means you can treat the problem of the number of movements as considering n minus 1 disks and the number of movements required for that to move n minus 1 disks from X to Z using Y, and the number of movements required for moving n minus 1 disks from Z to Y using X. So that's why you have 2 here. So one sub-problem, you have to solve two sub-problems. So that's why 2 into m of n minus 1, because you have to move n minus 1 disks. And what about this one? This one is again for this trivial step. And what about this? What about the base condition? See, when n is equal to 0, and here when n is equal to 0, this is known as your base condition. Okay, this is known as this as well as this is known as base condition. That means when the function will reach the base condition, it will stop. Every recursive function must have a base case resulting in a base condition in the corresponding recurrence relation. Otherwise, the function will enter an infinite loop. So remember, every recursive function must have a base case. Now this base case will lead to a base condition in the corresponding recurrence relation. Without a base case or without a base condition, the recursive function will enter an infinite loop. So here, when n is equal to 0, that means there are no disks. So if you don't have any disks present in any of the pegs, then you don't have to carry out any movements. That's why if you have no disks, there will be no movements. That's why when n is equal to 0, this function m of n will give me a value of 0 itself. Okay, so I hope you have understood the recurrence relations. Now, using the method of back substitution, I'll be solving these recurrence relations. So let's see how it's done. Okay, let's solve this recurrence relation. So here, what I'll say is, this is my equation 1. Now, I'll try to find the value of I of n minus 1. So what will be I of n minus 1? In place of n, I'll substitute n minus 1. Now, if I substitute n minus 1, what will I get? I'll get 1 plus 2 into I of, in place of n, if I substitute n minus 1, I'll get n minus 1 of minus 1, right? So I can directly write this as I of n minus 2, right? So this will give me my equation 2. Now in place of n, if I substitute n minus 2, then what will I get? I'll get 1 plus right? So in place of n, if you substitute n minus 2, you get n minus 3. Now, let's putting equation 2 in 1. That means equation 2, see, it's a term for in minus 1. Now in place of in minus 1, let's substitute this value. So I'll get I of n is equal to, in place of I of n minus 1, I'll get 1 plus, so in place of I of n minus 1, I can write this entire term, this right hand side. So I can write 1 plus 2 into I of n minus 2, right? Okay. Now if I expand this, so I am going to be, erasing the board and making the changes. So what I would suggest is, you please pause the video from time to time and keep on copying the steps. Okay, so in place of writing another step due to lack of space, I'll just make the changes here. So what will I do? I'll just expand this. So I'll remove the bracket, and here I'll get 2 into 1 as 2. So I'll get 2 plus 2 into 2, that is 2 raised to the power of 2. So this is my expression. And here the bracket is no longer present. Right? Okay. So now what I'll do is, I'll take this expression. Now see, this expression contains in minus 2. So now my equation 3 contains an expression for I of n minus 2. So I'll take this and I'll substitute in this equation. Let's call this 4. So now what I'll do is, I'll putting 3 in 4. So I'll substitute 3 in 4 and I'll get I of n is equal to 1 plus 2 plus 2 to the power of 2. Now see, I of n minus 2. I of n minus 2 can be written as 1 plus 2 into I of n minus 3. Now if I expand this bracket like I did here, so I'll just show this step for you. So I'll get 2 to the power of 2 into 1 is 2 to the power of 2. 2 to the power of 2 into 2 is 2 to the power of 3. I of n minus 3. So this is the expression I get for I of n. Now if I generalize this, then for the ith term, if I generalize this for the ith term, what would I get? I'll get 1. Now 1 can be written as, if you can rewrite 1 as 2 to the power of 0, then it will be easier for you to understand. 2 can be written as 2 to the power of 1. This can be written as 2 to the power of 2, and so on till 2 to the power of I into I of n minus I, right? Okay, see, the value of the power and the value of this 3 is same. See, here is 3, here is also 3. So these two, so if you generalize it, you will go up to the ith term. So this will be n minus I. Now since there is an I here, the power will also contain I. Now this is what you get after generalizing. Now the problem with this expression is it contains an I. Now you have to somehow remove this I and express this entire thing in terms of n. So in order to do that, look at the base condition. The base condition is I of n is equal to 1 when n is equal to 0. That means you can say that I of 0 is 1. I of 0. So you place, see, n equal to 0. So in place of n, if I substitute 0, I get 1. So that is the base condition. So that is the base condition. Now in order to remove this I have to achieve this base condition. So how do I do that? I'll substitute. I'll write the expression n minus I. So n minus I. So I can write n minus I is equal to 0. So n minus I is equal to 0, which can be rewritten as n equal to I. Now in place of I, if I substitute n, so in place of I, so I'm jumping steps, okay, I'm just making the changes here. You please write the separate equations for every line. Now what I'll do is in place of I, I'll substitute n. So here I'll get n minus n. So what is n minus n? N minus n is 0. So this entire thing becomes I of 0. And what is I of 0? So you see, I of 0 is your base condition. So in place of n, if you substitute 0, you get I of 0. And what is I of 0? I of 0 is 1. So this part, this I of 0 can be replaced by 1. So if it can be replaced by 1, this is the final expression that you get. This is the final expression that you get for your I of n, for your number of invocations. Now, if you observe this carefully, this is in a geometric progression. This is a GP series. Now, how many terms are here? See, the first term is 0 and the last term is n. That means there are a total of n plus 1 terms. There are a total of n plus 1 terms. See, because the starting term is 0 and the ending term is n. So you have to consider both, right? So to find the number of terms, you say that this is the last term minus the first term. And now since you're including the last term as well as the first term, since it's inclusive of the first term as well as the last term, you have to add a 1. So the total number of terms come out to be n plus 1. That is why I'm saying that there are n plus 1 terms. Now what is the formula for finding the sum of a GP series? The formula is S is equal to A into R to the power of n minus 1 divided by R minus 1, where R is your common ratio. R denotes the common ratio and A denotes the first term. A denotes the first term. So which is the first term in the series? The first term in the series is 2 to the power of 0. And what is the common ratio? Now see, to find the common ratio, you take any two consecutive terms. Say you take first term, second term, or second term, third term, or third term, fourth term, and you divide the larger term by the smaller term. So which is the larger term? If I take the second term and the third term, which is the larger term? The larger term is the third term. So if I divide the third term by the second term, I'll get the common ratio. So I'll get, so R is equal to, if I take the larger term and if I divide it by the smaller term, what will I get? 2 to the power of 2 is 4. 2 to the power of 1 is 2. 4 divided by 2 is 2. That means my common ratio comes out to be 2. Now I have my first term, which is 2 to the power of 0. I have my common ratio, so I can simply substitute the values. I also have my n. Here n denotes the number of terms. Here n denotes the number of terms. I found the number of terms to be n plus 1. There are n plus 1 terms. I showed you just now. So if I substitute these values in this equation, I'll get the final expression for I of n. So let's do that. I'll just erase this part. So I hope you're copying down the steps separately, okay? You please do that. Just to make things a little faster, I am erasing and showing you the changes. But for your examination purpose, I would highly recommend you to please not skip steps and show the working clearly. Okay, so let's see. Now, what will you get? You will get, now here S refers to your I of n. So your I of n will be A. What is A? A is 2 to the power of 0, that is 1, into R. What is your R? Your R came out to be 2. Your common ratio came out to be 2. If you remember, your common ratio came out to be 2. So that is 2 to the power of n. N denotes the number of terms. The number of terms is n plus 1. There are n plus 1 terms. So 2 to the power of n plus 1 minus 1 whole divided by, what is R? R is 2 minus 1. So what will you get? You will get I of n is equal to 2 to the power of n plus 1 minus 1. So this is the expression for number of function invocations. That means if you are given, let's say you're asked a question like this, that given 6 disks, find the number of function invocations required. So what would you do? You would simply substitute. Here n refers to the number of disks. Here n refers to the number of disks. So what would you do? You would simply substitute in place of n the value of 6. So you will get 2 to the power of 6 plus 1 minus 1. So that's 2 to the power of, so 6 plus 1 is 7. So 2 to the power of 7 minus 1, that is 128 minus 1, which comes out to be 127. So this is how this formula will prove to be useful. Now let's find an expression for the number of movements. So I've just shown a few steps for you. These two steps are same as the function invocation part, like we saw previously. Now what I'll do is I'll substitute 2 in 1. Why? Because there is an expression for m of n minus 1 in my equation 1. This is my equation 1. This entire thing is my equation 1, and in equation 1 I find that there is an expression, or there is a term rather, not an expression, there is a term m of n minus 1, and in equation 2 I can see that I have an expression for m of n minus 1. So what I'll do is I'll substitute. I'll write putting 2 in 1. So if I substitute 2 in 1, what will I get? I'll get m of n is equal to 1 plus 2 into, now in place of m of n minus 1, I'll write this entire thing. So I'll write 1 plus 2 into m of n minus 2. Right? Now if I expand this, what will I get? If I expand this, I'll get m of n is equal to 1 plus 2 plus 2 square m of n minus 2. Right? Let's call this equation 4. Now in equation 4, I can see that there is a term m of n minus 2. And in equation 3, I can see that there is an expression for m of n minus 2. So I can say putting 3 in 4. So if I substitute 3 in 4, what will I get? I have an expression for m of n minus 2. For m of n minus 2, what will I get? I'll get m of n is equal to 1 plus 2 plus 2 square. Now, in place of m of n minus 2, I have an expression for m of n minus 2. So in place of m of n minus 2, I'll substitute this entire thing. And I'll get 1 plus 2 into m of n minus 3. Right? Now, if I expand this, what will I get? So I'll just erase this part, or let this part be there. What I would suggest you to do is, you please copy down this part, and I'll erase the board and move on to the further equations. Now let's see this. So what I can do is, I can just expand this part. So I'll say 1 plus 2 plus, I'll just expand this. I'll get 2 square into 1 is 2 square. 2 square into this part. Into this part will give me 2 cube into m of n minus 3. Now, again, just like we saw in case of the number of function invocations, we need to get rid of the function part, right? In order to get one consistent expression. Now, before doing that, I'll just generalize. So I'll generalize up to the ith term. So I'll say generalizing up to ith term. So if I generalize up to ith term, what will I get? I'll get 1 plus 2 plus 2 square Now, like this, I'll get up to 2 to the power of I, right? So I'll just write the ellipses. Up to 2 to the power of I into m of n minus I. Into m of n minus I. Now, I have to somehow eliminate this I. And in order to eliminate this I, I'll use the base condition. I can see that the base condition is n is equal to 0. So I can say that n minus I is equal to 0. And if I equate this, I'll get n is same as I. Now, if I substitute in place of I the value of n, what will I get? I'll get m of n is equal to 1 plus 2 plus 2 square, so on till 2 to the power of n, sorry about that, into m of 0, because n minus n is 0. See, in place of I substituted n. I'll just show you. See, in place of I substituted n. So I get what? I get n minus n. Now, what is n minus n? N minus n happens to be 0. So I have m of 0. And what is m of 0? M of 0 is 0. See, in place of n, if you substitute 0, you get m of 0 as 0. So in place of m of 0, I'll get 0. So I'm skipping a few steps, okay? I'm erasing and writing. You please show the steps separately. So I'll get 2 to the power of n into 0. That means this term will completely vanish. This term will completely vanish, and I'll be left with the last term. I'll be left with the last term as 2 to the power of n minus 1. So look at this very carefully, okay? So my last term is 2 to the power of n minus 1. Now again, what I have is another GP series. So if you remember the formula, so the formula for GP series was a into r to the power of n minus 1 divided by r minus 1. Divided by r minus 1, where r is your common ratio, a is the first term, and n is the number of terms in your series. So how many terms are there in your series? Now, in order to find the number of terms, you look at the first term. So here, in place of writing 1, I can write this as 2 to the power of 0. This is 2 to the power of 1. So this will be easier for you to understand. Now look at the first term. The first term is 1, and the last term is n minus 1, right? So there are how many terms? There are n minus 1. So my last term is n minus 1, and if my first term is 0, so I can write this as n minus 1 minus 0. I'm just subtracting the powers, okay? N minus 1 minus 0. Now, since I'm including both the first term as well as the last term, I'll have to add a 1. So n minus 1 minus 0 is n minus 1 plus 1 is n. So this is how you find the number of terms. See, here you have the last term as n minus 1 and the first term as 0. If you look at the powers, then this is the 0th term, this is the first term, second term, this is the n minus 1th term. So you take n minus 1, you subtract 0 and you add 1. Why are you adding 1? Because you're including the first term as well as the last term. When both ends of the series are included, you have to add a 1. So the number of terms that you get is n. Now, what is the value of a? A is your first term. A happens to be 1. 2 to the power of 0 is 1. And what is r? You take any two consecutive terms and you divide the larger term by the smaller term. So if I take these two consecutive terms, the larger term is 2 to the power of 2 and the smaller term is 2 to the power of 1. So I will divide the larger term by the smaller term and I'll get 4 by 2 as 2. So my common ratio is 2. So now my m of n, can be expressed as that GP series. So what is A? A is 1 into R. What is R? R is 2. So into 2 to the power of n. What is n? N denotes the number of terms. Here n denotes the number of terms. So what is n? Here the number of terms is n itself minus 1 whole divided by r. What is r? R is 2. 2 minus 1. So this comes out to be 2 to the power of n minus 1. So this is the number of movements that you would require for n disks. That means given, let's say, 7 disks. If you're given 7 disks and if you're asked to find the number of movements required to move these 7 disks from peg A to peg B using peg C, what would you do? You would substitute in place of n this value of 7 and you will get 2 to the power of 7 minus 1, which is 127. So you will get 127 movements. So you need 127 movements to transfer 7 disks from disk A to disk B using disk C. I mean, you need 127 movements to transfer 7 disks from peg A to peg B using peg C. Now I'll finish off this video by discussing the time complexity and the space complexity. Okay, before I wrap up this video, I would quickly discuss the time complexity and space complexity of Towers of Hanoi. Remember, the time complexity depends on the number of function invocations. So if you remember the recurrence relation for the function invocations, for finding the number of function invocations, it was exactly like this. Now in place of I of n, I have used just T of n to denote time complexity, and everything else remains the same. Now, if you solve this, like we did earlier on in the video, we solved this recurrence relation and we found it to be this value, 2 to the power of n plus 1 minus 1. Now, if you take this term 2 to the power of n plus 1, you can get 2 to the power of n into 2 to the power of 1 minus 1. Now, out of these two terms, this is a term and this is a term, right? Out of these two terms, which is the leading term? The leading term is 2 to the power of n. So, only the leading term would be contributing to the time complexity. So in the worst case, you would get order of 2 to the power of n. That means this problem of Towers of Hanoi has exponential time complexity. It has exponential time complexity, right? So it takes up a lot of time. It has exponential time complexity. Okay? This denotes exponential time complexity. Now, what about the space complexity? Remember, whenever you're analyzing a recursive function and you're asked to find the space complexity, you would have to look at your stack. The stack that you're using for evaluation, that recursive stack that you're using, what is the length of that stack for particular values of n? So we find that we require n plus 1 stack records. So if you solve for any value of n, if you solve the Towers of Hanoi problem using the stack method, you will find that you would require n plus 1 activation records. If you remember from my recursion videos, I had spoken about activation records. Every function call that is pushed onto the stack is known as an activation record. Now it has been found that for n disks, you require n plus 1 activation records. And every activation record represents a stack record. So we can say that we require n plus 1 stack records. Now, if you require n plus 1 stack records, that means the length of your stack will grow up to n plus 1, where n is your number of disks. As a result, you can say that the extra space that you require is in terms of the stack, and that is order of n. Okay, so I hope this is understood. If you have any doubts, please feel free to leave a comment in the section given below. And please don't forget to go through the description section of this video. I have included a number of points regarding Towers of Hanoi, especially the history that goes behind it, where it is believed that there are certain, you can call them saints, or you can call them people with mystic powers, who are trying to move 64 disks from a tower A to a tower B using tower C. And the moment they complete moving all these 64 disks, the world will come to an end. So there is this little story. I'll share that in the description section below. You please go through it. And if you have any doubts, once again, you please leave them in the comment section below. Thank you for your cooperation. I'll see you in the next one. Goodbye.